All right, let's get started. So hello, everybody. Welcome to the LINCC Tech Talks. My name is Colin Chandler, and our co-host is Mi Dai. We're both LINCC Frameworks project scientists. I'm at DiRAC Institute at University of Washington, and Mi is at University of Pittsburg. So Tech Talks include presentations and demonstrations that showcase work done by the broader Rubin software science and archive community with the goal of furthering enabling LSST science. So unlike traditional talks you might hear at a conference, Tech Talks highlight the technical aspects of the work being done. We hope that these talks will provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in analyses of LSST data. The LINCC Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific. Joining us today is Craig Pellegrino, postdoc at the University of Virginia, Department of Astronomy. He's an active member of the LSST Transient and Variable Stars collaboration, as well as the LSST Informatics and Science Statistics Science collaboration. These are long acronyms. Craig studies supernovae, especially rare and unusual supernovae, in order to better understand the final stages of stellar evolution. What brings us to Craig today is over the last several years, he's also been interested in the intersection of time domain astronomy and data science with a focus on developing software for better handling the large data volumes that ongoing and future time domain surveys will entail. So Craig's going to give roughly a 40-minute talk, and we'll have plenty of time for questions at the end. So without further ado, Craig, please take it away.
Perfect, thank you. Let me share my screen. Okay, can everyone see this? Okay. Okay, so thank you so much for having me here today. I'm Craig Pellegrino. I'm a first-year postdoc at the University of Virginia, working with Professor Mario Mojaz. And today I'm going to be talking about some software work that I've done, both as a grad student and continuing now through my postdoc, developing this software called the Supernova Exchange 2.0, which is software to sort of better handle the follow-up of extragalactic transients in the Rubin era. So I kind of want to start just by sort of framing this talk in terms of the current state of time domain astronomy and what that means for Rubin. So the message I kind of want to leave everyone with is that current time domain surveys are discovering this exponentially increasing number of extragalactic transients each year. So I'm particularly interested in researching supernovae. So here I've just plotted the number of supernova candidates that have been discovered over the last 10 years. These are just candidates that have been reported to the transient name server, which is sort of like this bookkeeping service for extragalactic transients. And you can really see this sort of rapid exponential increase in the rate of discovery. This is primarily driven by surveys like ZTF, Atlas, Assassin, et cetera, coming online. And I really want to emphasize that this rapid pace is only going to continue to accelerate once Rubin LSST comes online too. It's predicted to discover something like 1 million supernova candidates each year. And so this has actually been really great for my research. Again, focusing on supernovae, these surveys and this accelerated pace of discovery has led to really big samples of supernovae of all different subtypes. So I'll just give like a really quick overview of supernova taxonomy, just because I'll be talking a little bit about the interesting science cases that Rubin will be useful for. So I'm sure many of you know supernovae can be broadly classified observationally based on their spectral features, so what elements their spectra do or do not contain. So very broadly, they can be split up into two categories, type 1 and type 2 supernovae that have no hydrogen or hydrogen in their spectra, respectively. And then we can break down each of these very broad classes into more and more different subtypes. There seem to be more discovered or announced every day. But sort of the big ones to focus on are these type 1As over here on the left. These are really useful for cosmological measurements, like measuring dark energy. These are observationally classified as supernovae that don't have hydrogen, but have very strong silicon in their spectra. And I'll talk about their physics a little bit more later. There are also stripped envelope supernovae. So these are massive stars that have lost their hydrogen and sometimes their helium envelopes. So characterized by spectra with no hydrogen and with or without helium, respectively. And sometimes we see narrow lines in their spectra, which indicate that their ejecta is running into some sort of pre-existing circumstellar material, producing these very strong narrow emission features. So you stick a little n after their classification names, and you get 1 BNs and 1 CNs. And then over here, we have the type 2s. These are hydrogen rich. These are the core collapses of red supergiants mostly. And they can be further broken down based on, again, the presence or absence of things like helium, narrow lines in their spectra, as well as based on their light curve morphology. So that's all supernova taxonomy. It's a bit like stamp collecting, so if it's boring, I completely understand. The main idea is that physically there are distinct things going on here. And that's interesting when you get, interested in stellar evolution theory and stuff like that. So really the outlier in this diagram are these type 1As. These are thermonuclear supernovae. So they're the explosions of white dwarfs. White dwarfs, if people don't know, are sort of the remnants of lower mass stars, stars with initial masses less than about 8 solar masses or so. When these stars run out of fuel in their core, they sort of gracefully shed their outer layers, and all that's left is this very compact, hot remnant that's a white dwarf. And so we think that these white dwarfs accrete material from some sort of companion star until they reach some sort of critical density or critical mass, at which point they explode. And again, these are very useful for cosmological measurements. They are very standardizable, so we understand their light curve behavior and their luminosity very well, which allows us to use them to measure out distances in the universe out to redshifts of like something like 1 or so. So that's the type 1A supernovae. Everything else on this plot are core collapse supernovae. So these are progenitor stars that have initial masses greater than or equal to about 8 solar masses or so. When these stars run out of fuel in their core, they collapse in on themselves and explode. And again, their different sort of observational properties have a lot to do with the properties of their progenitor stars at the time of core collapse. So again, these surveys have really built these big samples of all these different supernova subtypes, but I really want to emphasize that there are a lot of questions that still remain about their progenitors and about their explosion properties. So some of the big ones that are currently being investigated and that LSST will be really good for are things like the progenitor channels of type 1A supernovae. We know that they're the explosions of a white dwarf, but it's not clear whether the white dwarf is in a binary system with another white dwarf or with a main sequence or a giant star. And better understanding their potential progenitor channels is going to be really important because it'll inform their use as cosmological yardsticks. In type 2 supernovae and core collapse supernovae in general, there's this really sort of focus right now on understanding the ways that massive stars lose material in their last final years or so. We've observed a lot of these core collapse supernovae to have undergone a lot of enhanced mass loss during their final year or months before explosion. And that's really challenging to a lot of theories of stellar evolution. So it's important to get a better handle on sort of what's going on with that through supernova observations. And then finally, particularly for stripped envelope supernovae, there's this increased sort of question as to what role binarity plays in the evolution of the progenitor star and what impact that might have on the supernova observables. So despite these really big samples, a lot of the biggest discoveries that have sort of tried to answer these questions have actually come from really early time follow-up of a small number of interesting supernovae. And so sort of I'll talk a little bit about why early time follow-up is important for all of these different classes. So for core collapse supernovae, it's really important to get early time follow-up because that's the time at which the progenitor properties and the properties of the progenitor star's circumstellar environment are still sort of imprinted on the supernova observables. So I think this was best seen with this recent supernova that a lot of you might have heard of, 2023 IXF. This was the closest supernova to us in the last 10 years or so. It was a core collapse, it was a type 2 supernova. And because it was so close to us, it was caught when it was very young. And so a lot of different groups and a lot of different papers have published results on this supernova. In particular, there's this really nice spectroscopic data series that I'm showing here. This is focusing on the H alpha line in the spectrum. And you can see how quickly this sort of spectral feature evolves within the first week or so of explosion. And in particular, this earliest spectrum, the one in black here, which is taken at something like 2.5 days after the explosion, shows this really interesting narrow sort of off-center feature, this H alpha feature, which might indicate some sort of aspherical circumstellar material. And so this really wouldn't have been possible without these really early time observations of this supernova. For type 1A supernovae, early time observations are also really important. So I said before that their light curves are standardizable, and that's totally true. That's how we use them for cosmological measurements. But as we've discovered a lot more of these type 1A supernovae when they're young, we've also noticed a growing amount of sort of heterogeneity in their early time light curve behavior. So that's what this plot is showing. If you focus in on the first couple days after explosion in this inset, you see that some type 1a supernovae have this sort of bump in their light curve. This is predicted in a couple of different progenitor models and explosion models. One possibility is if the white dwarf progenitor had some sort of main sequence or giant companion star, and when that supernova ejecta runs into that companion star, it gets shocked and heated up, and then you see that as some excess luminosity, as this little bump in the light curve here. So again, it's really important to get these early time observations for these type 1a supernovae because it helps us use them better as cosmological measurements. And then going a little bit away from supernovae now and focusing on other time domain areas, it's also really crucial for multi-messenger astronomy to get early time observations. So in particular, following up LIGO alerts, LIGO detections of binary neutron stars, and looking for the electromagnetic counterpart to their mergers called kilonovae. There's only been one kilonova observed that's associated with a LIGO alert. And that kilonova, which is shown here, was first detected something like 12 hours after the merger. However, if we had gotten earlier data of it, we would have been able to better constrain its potential powering mechanisms, its ejecta geometries and compositions, et cetera. So multi-messenger astronomy is a really hot field right now, and there's this really increased push to get really early time observations of any sort of E&M counterpart to gravitational wave events. Okay, so that's the importance of this rapid follow-up. I really want to emphasize that multi-wavelength follow-up is important as well. That's because multi-wavelength observations sort of give this very complete view of the transient's full emission, its full spectral energy distribution. Different E&M regimes sort of give complementary views into the supernova's powering mechanism, its progenitor, and its circumstellar environment. So for example, X-ray and radio probe the circumstellar environment. The ultraviolet is really important at early times in order to estimate the black body temperature and infer powering mechanisms. Optical is important because something like 90% of the rest frame emission is in the optical. And then infrared is able to probe deep into the ejecta and sort of decipher different spectral features that we might not see as readily in the optical. And especially for Rubin, this sort of multi-wavelength approach is going to be even more crucial. And that's because Rubin is expected to discover a lot of these transients at higher redshifts. And so a lot of their sort of maybe rest frame UV emission is going to be redshifted into the observer frame optical. So getting a better handle on this full multi-wavelength picture is going to be really important. However, this is a really sort of difficult problem to do because it requires a lot of coordinated follow-up observations among different facilities. So for example, space-based resources like Swift and Chandra that look in the X-ray and the UV, kind of working together with ground-based surveys and follow-up resources in the optical and infrared. So all of this sort of leaves us with this technical challenge that we're faced with in the Rubin era, which is how do we find the most interesting transients among the millions of alerts that Rubin is expected to issue each night, and how do we coordinate the follow-up that's needed to make the most interesting scientific discoveries from this data. Okay, so now done with the science for now. Now I'd like to talk a little bit about the software work that I've been doing to get sort of ready for time domain astronomy in the Rubin era. So there are a few really big software needs that we need in order to maximize time domain science. The first is the ability to rapidly submit observation requests to robotically controlled and Q-based telescope resources. And this is really important because it's going to reduce the time between the discovery of the transient by Rubin or another survey and the time when we can get our first follow-up observations. And again, because that early time data, those early time observations are so important for a lot of these different science cases, that's going to really maximize the science that we can do with these transients. The second big need is the ability to programmatically filter and ingest different targets of interest. So this is really necessary because, again, Rubin is going to discover millions of transients. It's going to issue millions of alerts each night, which is just way more than someone like me working a 9-to-5 job can possibly parse through. So we really have to turn to software in order to identify the things that we should really be following up. And then third, we need a way of easily visualizing data and sharing among and between collaborators and collaborations. So this is going to be important as we try and pull all of these large volumes of data, not just from Rubin, but other sort of follow-up resources, other surveys, pulling them all into one place, easily visualizing it so that we see sort of the full data set that we're working with, as well as fostering sort of more community involvement and collaboration between different scientists and different areas of time domain science. And I think sort of equally important to all of these needs is the ability to sort of have some sort of customizable software package that wraps up all of these features and then distributes that to the time domain community in a way that different time domain scientists can use for their own research interests. So a solution that kind of meets all of these different needs is this idea of target and observation managers, or TOMs. So TOMs are sort of software that interface with all different aspects of the time domain ecosystem. So they'll interface with surveys and with brokers, with different follow-up resources, and with different scientists and collaborations. That's what sort of this little flowchart here is showing. This is a paper by Rachel Street and kind of proposing TOMs and the TOM toolkit. So the TOM toolkit is a software package that's being developed by software engineers and scientists at Las Cumbres Observatory. It's a very customizable package that's sort of meant to distribute all of these different TOM features to the community in a way that astronomers can use. So in a nutshell, the TOM toolkit is really a web application. It's really a website that has all of these different features that you might need to find and observe and visualize targets of interest. So this is what it looks like right out of the box. It's a website, and on this website, there are pages for things like the targets that you are following, the observations that you're submitting, and the data that you're obtaining. And if anyone's interested, there's the read the docs for more documentation here. So I really want to emphasize that the TOM toolkit is really designed with astronomers in mind. I know that as an astronomer, and especially when I was starting out this project as a second-year grad student, I really had no software background, no coding background. But the TOM toolkit really is meant to be as like approachable as possible. So it's a pip installable Python package, which is nice for astronomers. Lots of astronomers, deal with Python. The web design might sound a little bit hard to approach, but the TOM toolkit's based around the Django web design framework. So Django is another Python package, which is really meant for web design. It's very heavily documented with lots of examples and tutorials online. So it's very approachable in that way. The front end that you need to actually customize the web pages themselves, it's all easily done with HTML. And if you feel bold, you can get creative with CSS and JavaScript as well to mess around with that. And then the database backend is all through SQL. So astronomers generally have some experience with SQL. You can have a SQLite or a Postgres database backend. And the nice thing is that all of this utilizes Django's object relational mapper, which is all in Python in order to sort of dynamically populate a lot of the different target pages or different pages in your TOM. Okay, so what I've been doing over the last 4 or 5 years or so is developing this TOM called the Supernova Exchange 2.0, or SNEX 2. This was for my collaboration called the Global Supernova Project, which, as the name might suggest, involves time domain astronomers and supernova researchers around the globe trying to find and follow interesting supernovae. So you can kind of think of SNEX 2 like a Facebook for supernovae, where each supernova that we follow has its own target page. That's kind of like the one shown here. So this is for a Type 1a supernova, 2017 CBV, which I showed a little bit earlier. And the idea of these target pages is to sort of synthesize and display as much relevant information as possible in a very concise way. So I'll kind of walk through all of the different information that's kind of displayed here. You have things like the classification and the redshift that might be important. You have coordinates of the transient. Each of these different tabs brings you to another target page that has different features or displays different data. So for example, it has observation forms, which I'll show later, the images that we're obtaining, and photometry and spectroscopy plots. And then over here on the left, there are aliases, other names that the target is known as well as different science interests, so why this target might be interesting. You can mark yourself as interested if you are involved in like the data acquisition or the data analysis, or if you're thinking about writing a paper. And you can also post comments, sort of like posting on Facebook wall, about why this target is interesting, or if you're getting follow-up data. There are visibility plots here, which just show the air mass over time. at different sites that you can programmatically add to your TOM. So just being able to visualize when and for how long this transient is visible. And then down here, we are displaying LCO images that we've taken of this object, as well as an Aladdin viewer just kind of showing where it is in the night sky. Okay, so that's sort of an introduction to TOMs and to the work that I've been doing. And now I want to talk about some of the key features that I've developed for SNEX2, sort of with this focus for with the Rubin era in mind. So the first one is the ability to programmatically submit follow-up observation requests. So SNEX2 interfaces directly with the Las Cumbres Observatory, or LCO, global network. So LCO is this network of robotic telescopes that's spread around the globe. There are something like 22 or 23 telescopes at 7 or 8 different sites right now. And the idea of LCO is that at any time in the day, there is a telescope in one hemisphere that's in the dark and ready to take observations. And so if you find something that's really interesting and needs really high priority observations, you can get an observation within minutes on LCO. So SNEX2 will interface directly with the LCO robotic scheduler. So as soon as we press a button, SNEX2 will send an observation request to the LCO scheduler, and it'll schedule an observation on a telescope within minutes. So this can really, again, cut down on that lag time between the time of discovery and the time of first observations in order to really maximize the science that we can do. So LCO is sort of the workhorse of SNEX2. It's where we get most of our data, but it also has the ability to submit to other Q-based and robotically controlled telescope resources. So right now that includes Gemini and SOAR. There are also modules that are developed for MMT and SWIFT as well as basically any other robotic or Q-based telescope resource you can think of. And again, I just really want to emphasize that these rapid multi-wavelength observations are really important to maximize the science that we can do with Rubin. So how that looks on the actual SNEX2 front end, each of those target pages that I showed before has a number of these observation forms that you can fill out. So this is a form to submit a photometry sequence. So on here, there's a number of adjustable parameters that users can adjust. So for example, you can change the cadence duration and the cadence strategy. So this is a request to get observations every 3 days. And the nice thing about this TOM software is that it's smart enough to check when the last time we got data for this target was. And if it was longer than 3 days, it'll submit an observation request to get a new observation right away. And on the other hand, if it checks and we've gotten data recently, it'll then wait another 3 days before submitting another request. So there's also a number of other fields on this form that you can change. So for example, you can change the filter exposure time, like the exposure times per filter, the number of exposures. You can adjust things like the observation constraints. So for example, the maximum air mass that you want to schedule this observation at, as well as things like the proposal you're submitting it under, and the priority, et cetera. So another key feature I've been developing is the ability to filter alert stream targets and ingest potential candidates of interest. So right now I'm doing this all through user-written filters. So users can write their filters in SNEX2 that will interface directly with alert stream brokers. And I've sort of kind of tried to show how this works in this little flow chart here. So public surveys like ZTF and Atlas and Assassin right now and LSST in the future are going to be issuing alerts to different alert stream brokers. Sometimes they'll report directly to the transient name server. SNEX2 will ingest all of this information that it can. And then for any new target it ingests, it'll then run a few checks to see if it passes certain filters that users have written. So here I'm showing a couple of different filters that I've written just for my own scientific interests. These are designed to find supernovae that might be young and blue, for example. So it means that they're soon after explosion. And the fact that they're blue might mean that they're very hot or they have an interesting powering mechanism at early times. I also have filters to look for nearby supernovae just based on a redshift cut, as well as things that are rapidly evolving. So changing in brightness very quickly, again, might indicate that they're peculiar somehow or they have an interesting powering source. And so SNEX2 will just run a series of really basic cuts right now on all of these different candidates that it ingests. So it'll check to see if it's young, if it has a non-detection within the last X number of days, if it has blue colors, so a negative G minus R magnitude, if it's nearby based on some redshift, and if it's rapidly evolving, to see if it's changed in brightness. And if it passes any of these different cuts, it gets ingested under one of these different streams, and we can add it for more follow-up. So from the time that the candidate is reported to the time that we can actually run these filters, we've reduced that down to a matter of minutes. So again, we're really trying to reduce that lag time between the discovery and the first observations. And I should say that all of these filters are really customizable. So the ones that I'm just showing here are just for my own interests, but this is really, I think, applicable to all different areas of time domain astronomy. And users can really, there's really the flexibility for users to write their own filters to suit their own scientific interests. So on this NEXT2 front end, this is how it looks. We have this page that will display all of the targets from these alert stream brokers that NEXT2 ingests that passes these cuts. So this is just kind of shown as this HTML table here. Each of the rows in this table corresponds to a different candidate. And you have things like the coordinates and the names, as well as the name of the stream that it was ingested under. So for these are young and blue supernovae, for example. And then NEXT2 will try and pull as much sort of secondary information about this transient as it can from different sources. So for example, it looks for the redshift. It does a TNS query to see if it's been reported to the transient name server. It cross-matches with NED to see if there's a probable host galaxy that has a redshift in NED that it can pull from. And it also checks with different alert streams. So I think this Sherlock is running on one of the alert streams. It might be the Lasserre broker that tries and finds a best redshift for that transient. And it also does the same thing with the classification to see if it has a known classification from the transient name server. And if users are interested, they can just push a button and add this target for more follow-up at LCO. And then all of these different rows are expandable. So there are sort of air mass plots shown here, showing the visibility. There's, again, this Aladdin viewer showing the night sky, where it is in the sky, as well as these photometry plots. So NEXT2 will try and pull as much publicly available photometry as possible from different sources. So here we're displaying GR and orange band photometry. So this is pulling from both ZTF and Atlas. So again, NEXT2 checks every available photometry source to see if that target's been observed. It'll run force photometry if it has to in any force photometry server. And then it'll display it all here in these photometry plots to try and get the most sort of concise and complete view of this transient's early time behavior to see if it's worth following up. So we've been running this, or I've been running this since late 2022, so a little bit over a year now. And of all of the candidates that NEXT2 has ingested, we've added 95 or so for more follow-up in NEXT2, so for photometric and spectroscopic follow-up. So I'm kind of like breaking down the number by type over here on this table on the left. Of the 95, 38 turned out to be type 2s, and 32 turned out to be type 1as. But I really want to focus on these 3 categories down here. We've also identified 7 stripped envelope supernovae, 10 interacting supernovae, and 8 that were just classified as other, or we didn't know the classification, or were some sort of peculiar thing that we didn't understand very well. So these make up 25 of the 95 that we've sort of ingested for more follow-up. And these are really rare. So I think that it's doing a good job of actually finding things that are potentially interesting and that are, worth following up more in more detail. Some more statistics is that of all of these that we've ingested, 26% were followed up within a day of discovery. And if you expand that to 3 days, then that percentage goes up to 57%. And the median redshift of all of the things that we've sort of classified has been z equals 0.02. So again, our goal is to find things that are young and are potentially nearby. I think this is a pretty good first step. Again, just doing like very bare bones cuts on the targets that the alert streams produce. Okay, and then the third thing that I've been working on is the ability to share data and to better visualize it in the TOM. So NEXT2 has a number of different interactive plots on these different target pages, showing things like the photometry and the spectroscopy that we've gotten. So these plots are created using these Python packages called plotly and dash, which play really nicely with Django. And they're very customizable. And the nice thing is that they're all interactive in the front end for users to sort of toggle different options to display different data. So for example, for the photometry plot here, We have the option of displaying data by different instrument. So for example, we can display only the data that LCO telescopes have gotten. We can also toggle between unsubtracted and template subtracted photometry, where the template subtraction means that we've gotten some sort of image of the host galaxy and subtracted that host galaxy light from the supernova light to get a better estimate of the actual supernova emission. And then on the spectroscopy side over here, we have the ability to do things like plot the elemental lines of different elements. So for example, you can just plot the H alpha line on this plot, and you can adjust things like the redshift and the velocity in order to try and better classify the spectrum if it hasn't been classified already. And then this is a little bit of a prototype right now, but SNEX2 also has the ability to send and receive both data and messages through this messaging service called Hermes. So Hermes is this service that was sort of written for multi-messenger astronomy. Its goal was to have a place for time-domain astronomers to report things like observations and candidates of interest in a way that's all machine readable and can interface directly with TOMS. So the problem is that a lot of times in time-domain astronomy, things like observations or anything that's interesting was reported just through a text message or an email. That's very hard for machines to sort of parse through in a regular way. So this Hermes messaging system was sort of meant to try and enforce some sort of machine readable rules onto the communications that time-domain astronomers sort of issue. So right now, SNEX2 is listening to different Hermes streams that report things like multi-messenger alerts, so like LIGO alerts, for example, as well as GRBs. But Hermes can also be used to share data and observations between TOMs. So for example, if you are working with another collaboration and they have their own TOM, and let's say you want to send them a light curve that you have on an object, in theory, you can do that through a Hermes messaging stream if both your TOM and their TOM's listening to it. And you can really do that at a click of a button. Okay, so that's sort of an overview of all the different features that I've worked on. I kind of want to sum them up and give them an example using this multi-messenger astronomy as a use case. So I just want to start by saying that TOMs are especially crucial to multi-messenger astronomy, and that's for a number of reasons. They have the ability, again, to sort of programmatically ingest alerts and to submit observation requests programmatically or very rapidly. And again, this is really important in order to reduce the lag time between when this first multi-messenger alert is issued and the first electromagnetic follow-up observations that we can get. Again, that sort of plot I showed earlier of the kilonova light curve, it wasn't discovered until something like 12 hours after the actual merger. And we're really working hard to try and reduce that lag time as much as possible. TOMs are also really important because they sort of facilitate the ability of sharing observation plans and follow-up data with the community. This is really important because it reduces the number of redundant observations. And by redundant observations, I mean everybody sort of staring at the same patch of the localization region, whereas it would be much more effective time-wise to sort of look where someone else isn't looking to try and find the electromagnetic counterpart to the merger. And then finally, TOMs are just sort of collaborative by nature. The ability to sort of share this data amongst collaborators and collaborations, I think really prioritizes finding the actual ENM counterpart and doing the actual science rather than the competition of trying to be the first ones to say, look, I found this thing first. Okay, so we use SNEX2 also for multi-messenger astronomy. So despite the name, the Supernova Exchange, it's also used for gravitational wave follow-up observations. So the way it works is that SNEX2 ingests all the LIGO alerts that LIGO issues. As soon as it ingests one of these alerts, it'll create a target page for that alert, like the one that's shown here. So this page has information that's a lot like those supernova pages that I showed earlier. So for example, it has the name of the alert. It has relevant information like which LIGO detectors actually detected it, as well as the probability of it being different types of mergers, for example, a binary neutron star merger or a neutron star black hole merger. Then on the right here, it has things like plots of the distance probability, how far away this merger occurred, as well as the localization region where it occurred in the sky. And then it also listens to all of the different Hermes data streams and will pull all of the messages that it can for this alert and display them all in a very concise format here in this table. So these alerts, these messages have a lot of really crucial information about things like observation pointings that people are reporting or candidates that people might have found that warrant further follow-up. So all of that is sort of available at a glance here in this table. So once SNEX2 ingests one of these LIGO alerts, it'll then generate a ranked list of all of the galaxies within that localization region. So how it does that is it takes galaxy catalogs and it cross-matches it with the localization region that LIGO announces. And then for all of the galaxies that are within that localization region, it weights them based on things like its distance relative to the probability of the distance that LIGO reports, as well as things like its stellar mass, which we kind of use as a proxy for its probability of hosting the merger. And so SNEX2 will rank all of the galaxies in the localization region on those criteria, and then display them in this plot here. This is just a sky map, and each of these different black squares or black points corresponds to one of these galaxies in the localization region that we want to follow up. It'll also display it here in this table with lots of concise information, such as the score that our algorithm gave it, its coordinates, its visibility to make sure we can actually observe it, as well as important information about whether we've requested observations and whether data has been taken or not. So SNEX2, as soon as it generates this ranked list of galaxies, can automatically submit observation requests for the top N ones that we choose, basically. And then finally, if by some miracle we actually do observe the E&M counterpart, or even if we just want to report our observations, we can do all of that through SNEX2 as well. So we can do that through a Hermes stream. We can report all of that information back to the community through Hermes, or we can do it through other community resources. One such one is the gravitational wave treasure map, which is shown here that some people might have heard of. This is sort of like another TOM. Its purpose is kind of to conglomerate all of the different information that the community has on certain LIGO alerts, all of the follow-up information. So people can report their observation pointings and their candidates back to the treasure map, and it'll display it in a very concise way. So over here are each of these tiles is an observation pointing that one of these instruments over here has reported for the localization region. Okay, so that's a lot of sort of what I've done. And in the last few minutes or so, I kind of want to talk about future work to get SNEX2 really ready for the Rubin era and just sort of summarize what I've talked about. So a couple of next steps that I am planning on actively investigating in the future. The first is that I want to use the LSST Data Preview 0 data products in order to test some of the potential science goals that SNEX2 might be involved in. So the first is trying to reduce the number of false positives in the candidates that we ingest through different alert streams. So right now, a lot of those alert streams that I showed earlier, they get confused. They might think that something like a variable star in the galaxy might be a rapidly rising supernova, for example. And once LSST comes online and we start to build up all of these catalogs of variable stars and solar system objects, it'll be really interesting to be able to cross-match the candidates that we ingest with those catalogs to make sure that we're not just wasting our observations on a variable star, for example, if that's not our interest. Another science goal that I'm really excited about actually is the ability to combine data from different surveys programmatically. So I showed that a little bit. We're starting to work on that functionality with some of these alert stream targets that we're ingesting. But I think that ability is going to be really important for a lot of different science cases. One really exciting one is to search for precursor emission in LSST to really nearby core collapse supernovae that might be discovered by other surveys. So right now, we're sort of better understanding that a lot of these core collapse supernovae undergo a lot of enhanced mass loss in their final year or so before explosion. And this might show up electromagnetically as some sort of precursor emission to the actual supernova. So that was sort of, again, best exemplified by this object 23IXF, this really nearby supernova last year. So this here is a plot of all of its precursor non-detections, basically, before the actual supernova, which is up here. And all of these data points are just non-detections. We're just placing limits on it. But all of these different bands show what the sort of typical precursor emission should be for different types of supernovae. So for example, type 2N supernovae have pretty luminous precursors between absolute magnitude -12 and -15. There was this interesting type 2 supernova, 2020 TLF, which had a precursor around here, around -11 or so. And then all of these are non-detections for the progenitor of 2023 IXF. However, with Rubin LSST, this detection threshold is probably going to drop a lot more all the way down to here. So we can probably get a better sense on the percentage of these core collapse progenitors which actually do undergo some sort of eruptive mass loss or other luminous sort of mass loss episodes before explosion. And then I'm also interested in sort of better improving the alert stream filters in SNEX2 right now and getting them ready for Rubin. So one project idea I have in mind is to simulate the light curves of different types of supernovae in Rubin using this metrics analysis framework, and testing that on our current user-written filters to see how well we'd be able to pick up on those kinds of objects in the Rubin alert stream. And if any of those parameters that we set based on things like the rise rate or the non-detection threshold, if any of those have to be tweaked to sort of better identify these types of supernovae. I think it'll also be really interesting to incorporate some sort of machine learning classifiers into the data stream. This is sort of a really big push right now. Again, just trying to deal with the large volumes of data that we're going to be facing with Rubin. I think one thing that we could really use is more machine learning classifiers that are primarily focused on early time observations, rather than just waiting for when we have like a complete transient light curve and then trying to classify that. Again, because trying to catch these things while they're still young and get the best follow-up observations as possible, I think is really crucial. And I will say, I think that there's a growing number of these early time machine learning classifiers that I'm really excited to try and work with SNEX2 to incorporate. Okay, so here I'll just summarize. This is the outlook for time domain science with Rubin. Rubin's going to discover millions of transients, but in order to really maximize the science that we can do with them, we really do need rapid multi-wavelength observations. And I think software is really going to be key to filtering these candidates and to scheduling follow-up observations programmatically on these robotic and cube-based telescope resources. So some software that's sort of designed to, with that goal in mind is the TOM toolkit. And again, the TOM toolkit is extremely flexible. It's really meant for any use case in time domain astronomy. Any time domain astronomers can sort of customize it for their own scientific needs. So I've been developing this TOM called SNEX2, which is created with the Rubin era in mind, trying to focus on the follow-up of young and rare supernovae, as well as gravitational wave counterparts. And then if anyone's interested, SNEX2 is available on GitHub. It's all open source. There will be a paper coming soon, hopefully. And I just want to give a big shout out and thanks to all these people who have worked on SNEX2, and happy to take any questions. Thank you.
Awesome. Thank you very much, Craig. That was super informative. So we'll open up the floor for questions. If you're on Zoom and you want to raise your hand, if you're in a physical room and want to just wave at us, that'd be fine. Yeah, we have about just a little under 10 minutes for questions.
May I ask? Thank you so much for talk. Hopefully you could hear us here at CMU. Very general question. What technical challenges do you expect to have in Rubin era when you will have 1 to 2 order of magnitude more data?
Yes, that's a good question. I think that the strategy of ingesting everything we can into our database and doing everything on our end is going to quickly not be feasible, just because I think that the database that SNEX2 currently is running on is probably not suited to deal with 1 to 2 orders of magnitude more transients or data in it. So I think that's going to be a big push, is to sort of stop doing things on our end and do as much as we can on things like the Rubin Science Platform or other sort of outsourced sort of resources, I guess. Yeah, that's like the biggest one I can think of. And again, I think the other one is kind of switching from I guess we don't really have anything currently that's like Rubin, obviously. So I think right now a lot of these filters and a lot of these things that I've written are really focused for alert streams like ZTF, which again is focused on sort of more nearby supernovae just by nature, by its detection threshold. It has different filters. It has a different cadence. So I think it's going to be a bit of work to sort of adjust what we're looking for with Rubin in mind.
Awesome. Thanks, Costa, for that question. I actually had a related question, which was, you mentioned the numbers in one of your slides of how many detections you've had thus far. Can you give us like a ballpark of just how many items, elements, alerts, etc., that you had to filter through in order to get to those numbers.
Yeah.
Perspective.
That's a really good question. Yeah. So these 95 that I mentioned here, these are just the ones that we've sort of added for more follow-up. These weren't just the ones that were ingested. So all of the ones that just were ingested and passed these cuts, it's probably an order of magnitude more. It's probably, my guess is probably close to 1,000 over the last year, probably like roughly 3 a day. And a lot of these were basically just me filtering them out because I don't know, very arbitrary criteria. I don't think it was as young. It seemed like it had a higher redshift. So if it had a redshift at like 0.05 or 0.06, I probably didn't add it for follow-up if it wasn't very interesting, just because it probably wasn't going to be bright enough for a long enough time to get really good data on it, to be worth, adding to a sample paper or writing a paper on it. So yeah, that was one. That's a good caveat to this slide. Yeah, it's a good question.
Okay, great. Thank you. Any other questions?
Yeah.
Go ahead.
Sorry. Okay, I do first. So I'm curious, like, how do you handle like multiple brokers? Like, do you query all of them, or like you query just one, or like individually and then combine the results?
Yeah, that's a really good question. Most of this is running through LINCC right now because LINCC has the ability to write like custom filters in their actual web portal, I guess. So that's where I've been filtering most of these. We also do ingest everything that's reported to the transient name server. So all supernova candidates, we actually do ingest, and we do run checks on those to see if those pass any of these filters that I've written. That's most of it. So that's most of where we get a lot of like the other non-ZTF photometry from is the transient name server. So Atlas reportings, things like Gaia reportings too, for example, Pan-STARRS 1. And there is the ability now that this has been a recent feature, the ability to query force photometry servers such as Atlas, and I think eventually ZTF as well, to get force photometry on objects. So I think that's going to be the next sort of frontier is once a target has been ingested that passes these cuts, is to try and run force photometry as much as possible on it, and to do that like every day to see if our classification or if our interest in it has changed. It's a good question.
Thanks.
I was curious about the overall stability of SNEX2 in terms of like amount of maintenance on your end versus the amount of time that you actually get to spend doing science. Where is it actually running? Like, where is the hardware? If you do need to scale it up by a couple of orders of magnitude for LSST, what are your plans for doing that?
Yeah, that's a really good question. Yeah, this is definitely still in I would say like a beta phase. I've definitely so I've been working on it since my second year of grad school, so it's been about 3 or 4 years now. There were a lot of technical difficulties with it, so it was really written from the ground up, but it was also meant to replace this other sort of proto-tom that we had called SNEX, just the original SNEX. And so it was a lot of trying to interface or try and connect both databases to make sure both were in sync. The first year or so I started working on this, it was 90% this work and 10% science, I would say, which wasn't ideal. But yeah, I think the next challenge that you said is definitely going to be scaling it up. So right now the hardware, it all runs on a server at Las Cumbres Observatory. We have a little bit of cloud integration, a little bit of AWS integration in terms of things like we store like data products, things like that in the cloud. But I think if we want to get serious about sort of running, on an order or 2 orders of magnitude more data, we might have to rethink that strategy.
Gotcha. Yeah, that makes sense. I've got a secondary question, but I'll hold off for a second in case there's others.
Thanks, you, Drew.
Okay. Here on the slide, you call it 26% were followed up within a day, 57 within 3 days. Is that delay between initial decision to submit a request in the queue and the actual observation just due to the limited number of telescopes that are robotically controlled, or is there something else in the bottleneck there?
Yeah, that's a really good question. Yeah, so by within a day of discovery, I think I mean I or someone else pushed the button to submit follow-up requests, observation requests for this target within a day of its like reporting, within a day of its discovery. So yeah, data might have been attained like a little bit after that. I would say, yeah, the bottleneck is definitely a limited amount of telescope resources, yeah, which I think you could always say. I think it's also a bit of a challenge because of just some of the cuts that we made. Like we weren't always looking for really young things. We were also looking for things that maybe were changing in brightness very quickly. So those might not have necessarily been, we might not have an emphasis on really early time follow-up for those things, for example. But yeah, that number is definitely something that like I would like to go up. Yeah.
Sure. Do you anticipate that being more challenging as LSST comes online? I imagine that there's going to be other TOM systems that, other people are interested in other things, and they're going to be submitting to these robotic queues as well.
Yeah, definitely. I definitely expect so. Yeah, I think we're going to be very limited by telescope resources. I mean, we're already very limited spectroscopically in terms of how much we can spectroscopically classify and follow up. But yeah, I think even getting observations at cadences that are shorter than the LSST cadence is going to be pretty competitive too, I would say. Yeah.
Thank you.
Great. Well, with that, we're just getting towards our the end time of the program. So thank you again, everybody, for joining us this week. And so next month on April 11th, we will be hosting a two-part talk that'll have the results of the last LINCC incubator program. So this is detection, instance segmentation, and classification for astronomical surveys with deep learning, called Deep Disk, and I call a novel cross-matching tool. You can keep an eye on the announcements on Slack if you are on the LINCC Tech Talks channel there. And also on the LINCC email list from LSST. The recordings for YouTube usually posted within a few days, and so we can stay tuned for that as well on our YouTube channel. Thank you very much, everyone, for joining us, and let's thank again our speaker, Craig Pellegrino.
Thanks.
Thanks for having me.
Thank you.